Hi, I'm Peyton Dennis, and today I'm going to be discussing Lab 2 Charge Tapes Revisited, the line charge model. So, the objective of this lab was to model two charged pieces of tape exerting an electric force on the other, except this time we had to distribute the charge evenly across the length of the tape. This yields more accurate results. It's the exact same experiment we did before, but we're just not treating it as point charges. So, some important concepts would be Newton's second law, F equals ma, but we're going to be using F equals mg, with g being 9.8. We need to remember the electric field of a point charge, the electric force, and we also need to remember the superposition principle, which is where we add up all the electric fields to get the net electric field, E net. This helps us to find the charge distributed across the piece of the tape. Some important values and assumptions would be the length of the tape is zero point 0.2 meters, the mass of the tape is 0.0002 kilograms, and the separation distance between the tapes is 0.012 meters. We are assuming the air resistance is negligible, that the charge on each piece of tape is the same, and that the charge is evenly distributed throughout the length of the tape, and this will help us with our calculations later. Some results. So the system and the surroundings. So the system would be tape B, and the surroundings would be tape A, and also everything else around. So the results, we have to remember that the force of gravity is equal to the electric force. That comes in handy later. We found that the magnitude of the gravitational force, which is also Fe, was 1.962 e to the negative 3 newtons, and that the charge on one piece of tape was found to be 2.877 e to the negative 8 coulombs. And down below, I have a model. So the pink would be tape B, which is our system. The little white arrows would be the electric field coming off of that tape, because remember, we did break it into little tiny charges. That piece of tape is balanced because of the Fe and the Fg, and below it, as you can see, there is distance. Those little orange dots, that as representative of tape A, which is the surroundings, and like I said before, there is distance between them. All right, so the calculations, we use this formula and we take the values that we already know. We got Fe from GlowScript, which was what, like I said, 1.962 e to the negative 3. We already know the rest, like R, L, K. These are values we know. We can plug them in and we can find our new charge, which is 2.877 e to the negative 8. So now we have GlowScript. So here we have just all of our constants, like the mass, Q, the length, the distance. Down below where it says like R, R mag, R hat, and E, those are just our values and our formulas from the previous lab that we just have to acknowledge here to get a correct model. The top tape and the bottom tape, we just have to also have those for our model, where you just type in the axis, like the vectors, the mass, N being the number of charges that you're wanting to model. I chose to model 20. Um, and so these are just helpful for showing what the tapes are. So this is to show the electric force on the top tape due to the bottom tape, just a bunch of formulas like the E field, D cube bottom, D cube top, dot position, all of that. Once again, it's just to set up a correct model for the scenario that we're looking for. Down here, this is the part where we had to acknowledge or input our arrows. So like the force of the electric force, and then the force of gravity. One is going to be white, one is going to be yellow, one is going to be pointing up, the other is going to be pointing down, as we are about to see right here. The red is tape B, which is our system. The blue is tape A. This is exactly like the model we predicted when we drew it. The white arrow is the electric force, and the yellow is the force of gravity. The forces that we see here are acting on tape B, and tape B is balanced, and there is separation between tape A and tape B. I know it's hard to see here, but there is. And we did find, like from the previous lab, the charge on one piece of tape when we were treating it as a point charge was 5.6 e to the negative 9th coulombs. Now, upon further calculations and using a more accurate force, we found the charge to be 2.877 e to the negative 8th. So there is a difference here. So now we can compare these two models. As we can see, the model that we have here with the line charge, it's just a lot more accurate than treating them as point charges, because in actuality, the tapes are not point charges. Some sources of error, the charges on each tape might not have been equal or properly distributive like we assumed. Going back to lab 1, when handling the tapes and charge may have been lost, we have to keep in mind that the models in this lab are representative of the results I gathered from doing the lab experiment in lab 1, which once again could have errors in them. So discussions. What if you modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. So to answer this what if question, when modeled as a point charge, the amount of charge is 5.6 e to the negative ninth coulombs, but when using data from the line charge model, the charge on a piece of tape is 2.877 e to the negative eighth coulombs. The difference is about 134.8%. And then the line charge model, it's just like I said before, it's just much more accurate. So why? Why do these estimates differ? Which value is more likely to be closer to the real value and why? The models differ because they use different processes. For instance, the line charge model splits the piece of tape into a bunch of smaller charges, yielding a more accurate result. Because the point charge method treats the entire tape as one point charge, the results are less precise. This is all about precision. The line charge model is way more precise and better at modeling what is actually happening. So that's why. Thank you so much for joining.